So yeah, I guess we can start now. Um, so last time we were talking about finiteness and how awesome it is supposed to be. The main thing we saw is this theorem by Gabor that says that if we have any finite ring, right, you can realize it, you can present it as a quotient of a ring S that has a sort of amazing properties. It is regular, right? Well, the hypothesis is that this is finite, right? Then this exists, and this is regular, well, finite, and moreover, it has a p-basis. And in fact, the proof was constructive in the sense that we took generators of the Frobenius push forward of R, and we deformed them to become a p-basis for S, right? So we saw that the proof is constructive, and the only thing we were missing was that S is Noetherian. But then Derek put your reference where you can read it, or I said maybe I'm going to try to type it eventually. But I think from now we can move on. So the cool thing about this is that it tells you that the dimension of R is finite. So a finite ring, a finite imposes a very strong condition on the ring that, for example, Noetherianity by itself cannot give you. And the other thing, I didn't mention this, but it is that R admits a canonical module. R admits a canonical module. Module omega R. We'll see later what this is, but in general, canonical modules exist if and only if your ring is a quotient of a Gorenstein ring. Well, a regular ring is Gorenstein. We'll see that later. But then you can cook up this thing. It's very weird looking, but in certain X, let's say X module of R, Rs over S. And here you have to use the relative dimensions. Okay, to make sense of this. And so that's a very, very important consequence of this. This is perhaps more important than this, and we'll use that later. And this is wonderful because so there is already a sort of gold standard for what good rings are, and this is the notion of excellent rings. So here we have excellent rings versus finite. So remember that we're trying to impose these conditions to have a good setup for rings. And so there's already a gold standard, as I said. These are excellent rings. I don't know if you have heard of them, but in principle, it's an axiomatization of what a very good ring is. So you take an Noetherian ring and you impose a whole bunch of conditions and you get excellent rings. And so here we're going to use this replacement. That's the idea. And so this is an example in which finite rings are better because excellent rings not necessarily have canonical modules. So I wanted to cover this in a little bit more detail, but I'm just going to tell you real quick what is the comparison here, and you can read a bit more of this in the notes. But the point is that finite rings are excellent. Okay, so finite rings are superior than, let's say, what is believed is good. But the difference is not too big. Actually, there is a theorem of Kuhn's, another one, saying that if you have a local ring, is excellent if and only if it is, well, let's say plus the residue field is finite, is the same thing as R being finite. Actually, it is more or less in the notes and exercise, kind of to prove that you can go from here to here. This direction is not so difficult. The other one is the more involved one. But so the point is that a finiteness is essentially excellent. You know, it's that condition. So it's supposed to tell you that, you know, a finite rings is a very wonderful set of rings to work on. So the proof of this, as I said, is a little bit involved, and I don't think it's worthwhile getting into that, because the philosophy will be different, right? Like, so eventually we're going to be needing properties that excellence gives you, you know, to do certain things. For example, you want to do a completion and preserve equidimensionality, and a whole bunch of, you know, like technical things like that you could use invoking this. But you can get it easily just using the finiteness, right? So then we just do that and just forget about this whole thing. But it's a good thing to have in mind. Okay? It's just like telling you a finiteness is great. Okay? But we have already two concrete examples for that. So this is the reason why we work with the finite rings. Okay? And so now it's time to move on and introduce our first notion of singularity. Okay, so today we're going to start with section 4, and it's going to be about F purity, F place, and feathers. So the funny thing about Feder is that he quit math, and now he's a lawyer, but his name is all over the place. I think that's kind of funny. But okay, what we're going to do is try to weaken the notion of faithfully flat for Frobenius. This is going to be our first weakening. It's going to be a very strong weakening, and we're going to try to make it less weak later. But let's start here. So, okay, so, but first we're gonna make a whole bunch of general remarks about purity and splitness for general homomorphisms of rings. And then we're gonna apply that to Frobenius. So what is the thing? So to talk about this stuff, we're gonna consider an R algorithm. Okay, just two rings and a homomorphism of ring between them. So, as we saw the other day, it's convenient to call F the spectrum of theta that we can view as a map between topological spaces, or more generally as a morphism of schemes. And the other day, we saw that we get three functors at the very least out of this. The push forward, which is just restriction of scalars. This goes from S modules to R modules. And there is at least two ways to go the other way, which are the extension of the scalars and co-extension of the scalars. And the thing about that is that they are related by adjointness. So how is it? The pullback is the left adjoint of push forward, who is the left adjoint of F upper straight. Okay? So you have this guy here, and you have these two guys floating around, okay? In a very satisfying way. So remember that, recall that theta equivalently F as a morphism of the scheme, let's say that theta is flat if and only if the pullback is exact. You know that if you have an exact sequence, let's say, well, I'm going to just write in between three things. So if this is exact, okay, then the pullback has to be exact. So flatness means that exactness is preserved. Okay, so and what faithful flatness does is to add the converse. So we can say is faithfully flat if and only if the other direction holds as well. Okay? That tells you that in order to check flatness, you can do it after pulling back the long F. Okay, and we have seen already examples of faithfully flat morphisms, like the completion. That's going to be the most relevant for us. Because this means that if we want to check that something is exact, we can just pull back along the completion and verify things there where we have no tools. And actually, we'll see an amazing one today. Okay? I'm just refreshing a little bit what faithful flatness means. There are different ways to rephrase it. For example, you can say that theta is faithfully flat if it is flat and it is a surjection on the spectrum. Or that if you pull back a module and it becomes zero, it becomes a module you have was zero to start with. Just different ways to say the exact same thing. Okay? And we saw that for Venus is faithfully flat, exactly when the ring is regular. Okay, the idea is now to weaken faithful flatness. So we're going to have the first candidate, which is purity. So here's the definition of a pure or holomorphism of rings. So definition. I know that you may have seen this, but it's not so standard in first unit of algebra, so I'd like to refresh it. So we say that theta is pure if, okay, let me write this. I didn't say this the other day, but I should have. So we have this adjoinous relationship. You know that an adjoinous is defined by units and co-units, right? So I'm calling here the, what is it, the unit or the co-unit? What is this one? This is the unit. The unit is a natural transformation from the identity to this. This is the so-called unit of the pullback, push forward adjoinous relation, right? So this is the unit of this. But we can be very concrete about what this means. It's not like a mysterious thing at all. It's just important to put it into the right context. But what is it, right? This is simply you pull it back, so you get this, and then you push it forward. So you just let it be the same thing, but with restrictions. It's just that. And the map, right, is you take M and you set it to 1 tensor M. Right? Okay? So if it's pure, well, another way to think about this map that is useful is to notice that eta M is equal to eta r tensor m. What is this? What is eta r? Eta r is literally just theta. It's the map we started with, right? If you pull back r, you get s. And if you restrict it, you get a push forward f. It's just literally theta. Perhaps I should put here push forward, but it's the exact same thing, and you tensor with m. And m tensor r is m, right? So this is this map. So purity means that this is injective. Is injective. For all n. So it means that the map theta is injective, but it remains injective, you know, after any tensor product with any R module. Actually, I put it here an exercise that you may assume that it is finally generated. You may restrict yourself to that case. If it is injective after finally generated change, it's injective after all this change because all modules are limits. No co-limits of finally generated ones. And co-limits could be used with tensor products and so blah blah blah, kernels, blah blah blah. Okay, but this is the notion of purity. You may well call it universal injective. It is injective and remains injective after any base change. Okay? So that's what we want. We want the unit for this pullback, push forward adjoints to be injective all the time. So, okay. Any questions so far with this notion? Okay. Okay, now that's purity. And now what is a split? Let's come back here. What is a split? So the second part of the definition is that theta is split. Now for splitness, what we're gonna do is look at the co-unit of the other adjoint thingy. So if, okay. So let me put it over here. So let me do it in red because it's going to be a little bit of a remark. What did I do with the red one? So, so then we look at this. So we have this relationship, right? So out of this, one extracts a co-unit. So the co-unit, it's gonna have the shape. You know, it's like it goes from here to here, the identity. It's a natural transformation between functors, right? So, but more concretely, we can put here an R module n, make it space here, and R module n. And this co-unit is famous and has a name. It's called a trace. It's a trace of n. Okay. And so let's see what this is. What on earth is this? By definition, this is just hum over R from S to M. To define the unit in the other case, right, we took advantage that S has a 1. It's an R module that happens to have a 1. Here we're going to do the same thing, and S has a 1. So there is a very specific map from here to here. So if you have a map here, let's call it, what is a good name? I think we call it mu the other day. Elements in here. So we can take mu and send it to mu of 1. So this map is often called also evaluation at one. And that operation there is the co-unit for this adjunction. So a splitness is going to require that this is surjective at least for m equals r. So this is going to be a split if the trace of r, right, which is a map from here to here, is surjective. What does that mean in practice? Well, it means this. This is the neat way to think about it. But in practice, what does this mean? How can you make an interpretation of this? It means that you can hit one, right? It actually means that there exists a map here that is surjective. Or it also means that there exists phi in here, R linear, right? R linear, such that phi of 1 equals 1, right? And you see why the name of a split, because it means that theta is split as an R modulo map, right? In other words, what this means is that you go and look at theta. It is a ring homomorphism, but in particular, the definition is R linear. It's a homomorphism of R modules. And so here you have phi to R, and what we have is that there is a phi such that this diagram commutes. So in other words, theta is split in the category of R modules, right? That's why it has the name. And this guy here may be referred to as a theta splitting. Is that okay? And actually you see the following. What is the relationship between a splitness and purity? Is that the splitness, what do you think, is way stronger than purity? So splitness, let's say split implies pure. The way to think about split is a cheap way to be pure. You want to be pure and you don't have much money, then you just impose splitness. Okay? And we'll see that splitness is not a good property, pure is. Splitness is not so much. It doesn't behave so well unless you impose strong conditions or certain conditions. Okay, how does this work? Well, it's hitting you in the face, right? What you do, take this diagram and just tensor it by m. Take this, right? And tensor it by m. What you get? You get m, and what is theta tensor with m? It's just theta, it's just eta m, right? And then you take phi, and phi is just, well, phi tensor m, and it's gonna be a map from here to m, which just exploits that m is an R module. This is just, if you have S tensor m, it goes to S times m, which this is the structural map, right? Well, not the structural one. Well, you also have to tweet by phi, sorry. Yeah. So if you have S tensor m, here this goes to phi of S times m. and here you have the identity. And so you have that eta n. It's not just injective, it's split, right? Because if you have such a condition, it implies this is injective, right? Any map that splits is injective, right? Splitness is just chip purity. Okay, now what is the relationship with faithful flatness? The relationship is that faithful flatness, well, let's put it like this. The idea is that purity is a weakening of faithful flatness, okay? So let's put it as a proposition. Again, just let's take on our algebra. And so if it is faithfully flat, then it is pure. So how does this work? Let's do the proof. Okay, so we got a proof that this is injected, right? That's the definition. For all n. How do you exploit faithful flatness to do so? Injectivity is a notion of exactness, right? It's immediately if I put 0 over here, the whole thing is exact. So what can I do? I can use faithful flatness and just say, okay, I'm gonna do it after pulling back with m, right? So this is injective actually, if and only if its pullback is injective. But what do you think? That's not just injective, it's a split. Therefore injective. How on earth is that a split? Well, it's built in all these adjoinance relationships. So the point is, actually, this is exercise 3.7, which is from the previous chapter. To prove, that eta is the unit. The unit for the adjoinance, it is because there was also a co-unit. That one in the notes is denoted by epsilon. So recall. So the co-unit of, put back here, push over here, is, we call it epsilon, epsilon, and so it's supposed to go from pull back, push forward, let's say epsilon m, okay? It's a natural transformation to the identity, right? So the co-unit goes to the identity, the unit goes from the identity. Okay. And how does this work? This is super explicit, right? So what on earth is this? So, oh, sorry, this is not an m, this is bad notation. There should be an n, right? Where n is an S module, right? So, well, you can take an S module and you can look at it as an R module. Sorry, I need to write it now. And then you can tensor it by S. That's not an issue, right? But then you can exploit that it was an S module to start with, which means that it comes with a structural map here, right? There is a bilinear pairing between S and N that goes to N, right, which is the scalar action, and therefore there's a canonical tensor map with a tensor product here, right? If you want to be super explicit, this is none other than this. Okay? But there is this cocycle condition that one has to verify to check that these things define an adjoint relationship. And one of them is that you can take, look at this, now I'm going to take N equal to the pullback of N there. So I can write down here epsilon pullback of N. And I go to pullback of N. And actually, the fact that you have an adjoint means that this commutes. So this map always splits this. And that's why faithfully flat extensions are pure. You use the faithfully flatness to say that you can pull back your situation to a setup in which abstractly, by just pure abstract nonsense, you have the splittings already, and therefore injections. Okay? Yeah. So it's a whole bunch of pretty abstract nonsense that you have to let sink in. But that's the way to do it. Okay? So, any questions so far? Maybe on Zoom? I hope this is fun. It's fun commutative algebra. So, however, so let's summarize what we have. We have purity. Purity. We have faithful flatness. And you write it down like FF. And we have the splitness. And we have this relationship. However, this converse is far from true. It's just far from true. Okay. So example. Actually, I think any completion works. But let's take the easiest completion I can think of. Let's take the integers, localize a primary P, P non-zero. Okay. It's a prime number. And let's take the completion, which goes by the name of p-adic numbers, right? It's just a p-adic completion. So these are the p-adic integers. P-adic integers, which are literally the completion of that thing. This is just the completion map by definition, right? So this is faithfully flat because this is faithfully flat yet because it is a completion, therefore it is pure. So this is faithfully flat, so pure. Sorry, the one I was saying that this is not true in general, but not a split. So for this, I'm going to get to that as an exercise. Yeah, later on, we'll see more examples in which this is just not true. We'll have a billion examples of this, okay? This is a very strong weakening of faithful flatness. Yeah, sorry, what I want to emphasize is that this is not, the converse is just not true. Okay. Another exercise that I would like to write down to emphasize the point here. I'm coming here with an agenda, which is to tell you that splitness is not a good notion. purity is. Purity is a real notion here, okay? So for example, look at this. So you have that this map is pure, respectively, faithfully flat, if and only if all its localizations are pure, respectively, faithfully flat for all prime ideals in the spectrum of R. Okay, so you see that purity and faithful flatness are geometric notions. They localize well, so to speak. Okay? So for splitness, so let me put it here maybe in a different color. What happens is the following. So let you do that as an exercise. If your map is a split, well, you can localize that map and you can conclude a splitness here. That's fine. If you have a split globally, you have a split locally. What is not true is the converse. And that's the tricky part. Like if you have a whole bunch of local splittings, there is no reason for you to be able to glue them together to a global splitting. Okay? Not possible. And the actual reason is because home not necessarily commute with flat base change. That's the issue. Let's see why, right? And that's a very important point to make. And again, it's gonna come back all the time. And it's a source of mistakes for news. Okay, what goes wrong with the splitness? And it's right here in the definition. Right? You may think, right? Okay, so well, let me write it down again. What could go wrong with the splitness and localization? Because all I have to do is that the map is surjective, and I can do that locally, right? Because all I have to do is to prove the certain co-kernel is 0, which I can localize and blah, blah. But you have to be careful, right? Because, so, what goes wrong with splitness? So, by definition, what you gotta do is to prove that this map here is surjective, right? You said, wait a second, I could just localize and that's fine, right? And you certainly can do that. So you have to prove that this is surjective, and that's equivalent. You can do it locally. That's true. So you can say, okay, this is surjective. True, if and only if RP. What is that map? Is RP tensor hum R SR. RP is surjective. That's true. However, here is the issue that you have to commute a faithfully flat operation, certainly. Well, not faithfully, it's flat operation, it's not faithful. Localization is flat, but it's not faithfully flat because it's not surjective on a spectrum, right? That's the point of localization. You look at a restriction to an open. So right, so it's not surjective on a spectrum. So you look at this, and okay, well, certainly there is a canonical map from here to what you want. So you go here, and yeah, I think on Zoom you can see. So you go and look at this other object here. And there is a canonical map, right? Which is essentially well, I can, since it is RP linear, all I have to do is to tell you where to send a map here. So if you have, well, this map is defined by taking phi in here, a map here, and just localizing it here. So PP, which is phi tensor RP. So if you take a map that goes from S to R and you localize, you get a map that goes from here to here. And then you just extend by linearity. Actually, in other words, I'm doing a joiners of tensor with hom to define this map like that. Okay? So there is a very well-defined map, and actually, you have a trace here, which is a trace of RP, and this one commutes. That's fine. What is the problem? That this may not be an isomorphism. Well, the issue is that it may not be surjective. Okay? That's the issue. That hom doesn't have a good behavior with respect to flat base change. So this may not be an isomorphism or surjective. In this case, actually, it's always injective. This is specifically what feels is surjective, but may not be surjective, let's say that. It's not true that every map here is going to be a linear combination of localizations of map like that. So, yeah, sure. If you know that all of these maps are surjective, you have no reason to believe that this one is going to be surjective. Okay? Does that make sense? So, but when is hom well behaved with respect to flat base change? Well, there is an example of a good behavior, and this is the only good one I know. And I think anyone who has tried to extend the theory of F-singularities to very general setup has a struggle with this exact phenomenon that I'm going to write down. So it's this. So, well, here in the notes is an exercise that you have to do for sure if you haven't done it already. So let's take a ring R, and a ring, and let's take M and N are modules. Okay, and let's take T on R algebra. Okay, and so there is a canonical morphism. There is a canonical map from here. You have a set of homs, and N are linear map from N to N. You can go to T linear maps, and what you do is that you base change all these modules. And so this is defined by sending one tensor phi to phi tensor T. Okay, that's how this map works. It's a canonical map, very well defined. And when is this is an isomorphism if it's not an only if, it's just if at least two things. And well, here, you know, our convention is that everything is Noetherian, right? So, but even if R is a Noetherian, all you need is that N is finally presented. If R is Noetherian, then this means that it is finally generated. It's the exact same thing. And T is flat. T is flat. And so how does this work? Well, there is a case in which this is true, trivially, which is the case in which M is free. Okay? And then what you do is that you say, okay, let me say that M is finally presented, and you write down a presentation of M, which is this exact sequence, right? It presents M as the co-kernel of a matrix between free modules. and then like you write down what you need, and you use TS flat to kill some X, and blah blah blah, some Tor, sorry, and there you are. So you reduce it to free case using this hypothesis where this is trivial. That's the whole point of the argument. Okay. So you conclude that. So what is the conclusion here? If your algebra is finite, right, then splitness localize well, right? So the conclusion is conclusion. Take R2S finite, meaning, of course, in this one is here, okay? Always. So this means that S is a finite generated R module. Okay? Then theta is a split. If and only if theta P, say RP plus P is a split for all prime ideals. Okay? This one is always true. What matters is the order. Okay? But you see, you need some finiteness condition for this to work. And of course, here the point is that you need always to keep in mind forbiddance. We're going to apply this to forbiddance. Any questions so far? Now, so we start to see that perhaps if we impose finiteness, well, we see that the splitness has a good behavior, like purity. You may wonder, like, if finiteness is enough to guarantee that the split and purity are the same thing. It's true, but we still need another ingredient to see that's the case. And that ingredient is matrix duality. Have you heard of that? Matrix duality.
Oh, yeah.
Okay. No? So this is a truly remarkable and important theorem in commutative algebra that we're going to see real quick right here. So matrix duality tells you that the category of R modules over a complete local ring is truly special. So let's see. We may come back to this, but I don't know if we have the time to prove this thing, but otherwise we just use this as a black box. So, matrix duality. So if you have never seen this in your life before, be prepared to be amazed. And because it's amazing result. It's unbelievable. So matrix duality. And your life is going to change after this. You won't see the world in the same way. What is this? By the way, during the notes, I give you a reference where you can go and read the details. And actually, it's an appendix of a book, the 24 Hours in Local Cosmology book, the appendix. It's wonderful. So you will learn the details. So for this, let's start with a complete local ring. And thirdly, we need every characteristic. Actually, I don't know what's the deal with matrix duality and its characteristics. I haven't heard of that. But so any characteristic. Okay. In other words, R has a copy of K inside it that maps isomorphically to the residue field. Okay. And so we do that, and here I'm going to write down the start of the show, which is the injective hole of the residue field as an R module. So let's E. In principle, it should be E of K or something like that, or E R K. But let's just write it down by E. B. Let's put it in here. So let's say that it is EK, but it should be E RK. Should be the better name. B, the injective hole of K as an R module. Right? K is R module M, so it's an R module, and so it has an injective hole. What on earth is that? Well, it's in a sense the smallest injective module that contains K. It exists and it's unique, up to non-unique isomorphism. So it doesn't matter too much what it is. What matters are the formal properties it has, which are truly remarkable. So if you study the theory of injective modules, you will see why this makes a whole bunch of sense. So, but let's say, so what is that? So, IE. So E. So there are two things. E is an injective R module. It's an injective. Well, it contains K. Okay. So the first thing E has is that it contains K and it's injective. It's an injective R module. That's the first thing you want. What does injective mean? It means that the functor homing to E, if you home to E, it gives you a contravariant functor, is exact. Exact. And second, it's the smallest in the following sense. This means that it has there are no essential extensions in between these two things. But in practice, this means the following. So if you have N inside E, let's put it N, R module, okay? Non-zero, then N has to intersect K. So this is injective, and this is the whole part. So it's very snug around K. Right? What does whole mean? In Spanish, it translates to something like cascade, right? It's like the smallest thing arrived, you know? So it's like you put an injective module that covers it, and then you extract all the air, and you get like that tightness into it. And that's the spark. Okay? So remark. Well, this has nothing to do with K. You can put here any module whatsoever. Okay? And you can make it the same definition. And that's going to give the notion of injective hole of a module. So the point is that it exists and is unique up to non-unique isomorphism. So it is similar to algebraic closures of fields, right? You know that the algebraic closure of a field exists, and it is unique up to isomorphism, but not up to unique isomorphism, which means that the algebraic closure is in no way a canonical object. Okay? Same thing with injective hole. It exists, is unique up to isomorphism of R modules, but the isomorphism in between two injective holes doesn't have to be unique. So it's not canonical. Okay? Which is a big sad, but okay, that's life sometimes. Mysterious ways. Okay, and so you may be wondering, who cares? And we care because of the following truly outstanding theorem. It's a miracle, in a sense. Okay, so we have E, it's home into it is exact. That's all great, but what else? So, one more piece of information. Okay, let me just say this. So so more notation. So let's call M the category, the full subcategory of Noetherian. In other words, finally generated, because we're working over a Noetherian ring. Okay, but Noetherian are modules, are mods. Okay. In other words, finally generated are modules because we're working over a Noetherian ring anyways. Okay, but conceptually it's more satisfying to say that it's Noetherian, meaning that the lattice of submodules satisfy the ascending chain condition, blah, blah, blah. And then let's take A, the one of Artinian modules. Artinian modules are those modules over R whose lattice of submodules satisfy the descending chain condition, right? If you have a chain of submodules that go down, they eventually stabilize, right? It's dual to Artinian. However, well, this category is very well understood, but this one is not so much in a sense, right? Like it's like what is, because right here we know it's finally generated on module, but what is this, right? And actually this theorem sort of tells you that it is as rich as this one. We'll see. So the next thing is to define the dual functor. So this is going to be the functor which is humming into E. Okay. In other words, you take a module and you send it to its dual. Its matrix dual. This is called matrix dual. So the matrix dual of N is this thing. All possible hums into E. Okay? So this is just notation. Notation. The substance is here. So first of all, we may restrict D to the category of Noetherian modules. You may wonder, okay, what happens if I take an Noetherian module and apply its matrix dual? What do I get? Well, it turns out that E, well, I didn't say that, but it's an Artinian module. So this is Artinian. Okay. This is a theorem that the matrix dual of an Noetherian module is Artinian. Okay, it's essentially because E is Artinian, so to speak. So for example, the matrix dual of R is E, because hums from R to E are elements of E, right? We've seen that before. So for example, here you can see easily that R goes to E. Okay? A very Noetherian R module goes to an Artinian one. Okay? Yeah, well, actually E is Artinian if R is Noetherian. And you may wonder what happens if you take an Artinian module and you apply D. What do you think you get? Well, it turns out that you get an Noetherian one. And so Notice that D is contravariant, right? So it reverses all the errors. So what we just wrote makes sense. D is contravariant. Now here's the little miracle. What happens if we do the following? So we take Noetherian, apply D, we get Artinian, and we apply it again. Why do you think this whole trip is naturally isomorphic to? Well, it turns out to be the identity. So, I guess the people in category theorize all sort of things, but let's just say this. There is a natural isomorphism between the identity and DD. Put in very simple terms, if you have an Ethereum module, there is a natural isomorphism from D of M. And what is this whole thing? It's a whole bunch of homes, right? So it's home of home. What is it? M to E, and then you do it again. A simple example would be the fact that if you put here M equals R, and this is something we're going to use. And actually, this here is based on this one. This is the most important one. Is the fact that when you look at the endomorphisms of E, right? You know that you can this canonical map here, right? Which is just multiplication by R. Just send R to the map that is multiplication by R, right? Let me just write down like this. You take, from E to E, you can just multiply by R, and you get an endomorphism. The magic here is that this is an isomorphism. Any other endomorphism of E is necessarily multiplication by R. That's the, great piece of math. And you extend this to that. Okay? We're good. That's the first part of matrix duality. I'm not done. The other part is the following. So is what happens if you go Artinian, Noetherian, Artinian. Well, same thing. Here you have the identity natural transformation on the category of Artinian modules, and the point is that there is a natural isomorphism between the identity and the composition with D itself. So, in other words, it's the same thing. Yeah, same thing. If you put an Artinian module here, when you apply its double dual, you get the same module back. Okay. So, for example, this tells you this picture, right? So, R and E are matrix dual to each other, and well, let's put it here. In other words. In other words, D induces an anti-equivalence. Is anti because it's contravariant, right? Between A, the Artinian R modules and Noetherian R modules. That's it. Over a complete local ring. That's what I was saying, over a complete local ring. The category of finally generated R modules is very special. It happens to be anti-equivalent to the Artinian one. So you see that in particular the category for Artinian R modules is very rich. It's as rich as the one of finally generated R modules. Okay. So that's very special of complete local rings. This is perhaps, I think, well, could be the most important reason why complete rings are awesome. Because this extra structure, this duality between Arcana and Ethereum. And we'll see more. We're not done. So we'll see later local duality. In local duality, it's going to be a tool to compute matrix duals, but not today. So let me give you an example. How are we doing with the time? Should we just stop the matrix dual more? It's just the proof that follows is example. I'm gonna give you this as an exercise. Example. We're gonna do this. So this is one of the typical examples. So if you have here a finally generated R module, this is matrix dual to E tensor. Okay. This follows from a joint between tensor products and homes. So I just want you to appreciate the beauty behind this because it lets you transform home into a tensor product, right? So you see this duality. And why is this duality useful for what we want, right? Because we want to compare splitness and purity, and purity is about objectivity, and splitness is about subjectivity, right? How do you swap them? And that's where duality is going to come in. There is one more thing I would like to say about this duality, which is that it's, so I started assuming that R is complete, but you don't need that to do any of this. Well, completion only plays a role in saying that the D squared is the identity. More generally, what you have is that when you apply D twice, you get that it's naturally isomorphic to base change completion. So more generally, what you have is a natural isomorphism between these two things. Okay. So if you put here any Ethereum or Artinian module, this is what you have. And so what's your completion to say that this is the identity? Okay. But this is going to be important because of the following. It's a very important observation. What would this say? In particular, this means that our hat is isomorphic to home. I'm just applying here this to R, right? So it means that when you look at the endomorphisms of E, it's isomorphic to R hat. That's the content here of this thing. Because look at it. It tells you that if you have an injected hole of the residue field of R, it is automatically an R hat module. What is an R hat structure, R hat linear structure, R hat scalar structure on E? It's just a map from here to here, by definition. It's just a way in which this ring can act on E by endomorphisms over R. Right? This says that the scalar structure extends automatically. And that's a miracle here. Because actually, you see that this means that an injective Hall of K over R is the exact same thing as an injective Hall of K over R hat. That's very important. So in particular, you can just go ahead and say things like, let's say the injective Hall of K, and someone may say, over which ring? And what do you say? Doesn't matter. Over any, it's the same notion. Why? Okay. So that's what's going on behind this matrix duality nonsense. Now, why is this useful? Do we have the time, perhaps? Yeah, I think so. If we are elegant, we can do this in 5 minutes. Okay, so that's all I need to know about matrix duality so far. So, matrix duality has the following corollary proposition. Take theta. Now we're going to assume the source is local, our algebra, but we're going to assume that this is complete. Let's see what happens. So complete, an equicharacteristic, okay? So that we can apply matrix duality. Then the following are equivalent. First, theta is pure. Remember, that means that you have to check that a whole bunch of eta enter injective. You don't need to do it for all of them. It suffices to do it with injective holes. The eta of the injective hole, which is this map, is injective. C, theta split. Okay, so this is obvious. This by definition is just for all n. So here you just have to check it for one of them. So cool, isn't it? So we are missing to prove that this one implies this, and well, this one is obvious, right? We just saw it. So all we're missing is this. Let's do it. It's just a matrix duality, believe it or not. Okay, so how something being injected translates to something being surjective, you may ask, right? That's what I'm claiming. The injectivity of something equals the injectivity of something else. And R is matrix dual to E. And you know, a split means the trace is surjective, the trace of R. Let's do it. So let's look at this. In fact, the whole point is, so actually, in fact, what is happening here in short is that, just as a remark, because it's a remark, if S, or let's say theta, is finite, so that S is Noetherian as an R module, then matrix duality says that the trace of R is matrix dual to eta E. Matrix. And so this is injective if and only if this is surjective. This is a truly important fact. This is going to come up all the time, because F singularities, you know, are going to be based on this, the trace. But very often we're going to transform them by matrix duality into certain injectivity stuff. Okay, so this is going to be the first instance in which this duality show up. The trace is dual to eta. Okay, however, we cannot use this because we are not assuming that S is finite. So technically speaking, we cannot just do this as it is, but still, we still have a lot. So okay, assume that eta E is injective. Is injective. You can just go ahead and apply D. Apply it, right? This thing is still this. It is still exact. Sure, it may not respect anything in terms of Artinianus and heterogeneity, but just apply. It is exact. Therefore, D of eta E, which we suspect is a trace, is surjective, right? Or let's just write down this E is surjective. This just uses that E is injective. E injective literally means that this functor is exact. So if this is injective, it has to transform into something surjective because it's contravariant, right? It's preserved exactness, but you have to switch everything. So something that is exact onto 0 is going to be exact from 0, or the other way around. Okay? So injectivity is transformed to surjectivity. But now, what on earth is this? I claim that is the trace. Still, let's see. Okay. Now, what we're gonna do is to look at the trace. So I'm claiming this is the trace, so let's look at the trace. So this is the map I want to prove is surjective. Okay, this is the trace of R. But R is isomorphic to this. Right? That's matrix duality at its heart. All the endomorphisms of E, oh, sorry, people of Zoom. So this is an isomorphism. All endomorphisms of E are multiplication by R, matrix duality at its heart, right? So the map that sends R to multiplication by R is an isomorphism. Okay, so what is D of eta E? Well, D of eta E over here will have hom R S tensor RE, comma E, right? And this map here is D of eta E. This contravariant, so you have to switch the order of the arrows now. So remember, E went from here to here, but when you hum into it, you have to switch the direction. And from here to here, we have the following map in which you can just take a map here, sigma, that goes from S to R, and you can just tensor it by E. You get a map from here to here, right? I claim that this diagram is commutative. Right, commutative, not Cartesian. That's a very simple calculation. But there is no reason to believe that this is an isomorphism. If S were finite, it would be by matrix duality. That these two things are matrix dual to one another. That the matrix dual of this thing is this thing. But let's see. What is this thing? Let's use the adjoint between tensor and hom to write this down as this. Hom are E to E. These two things are certainly not equal, what you can call equal, but by the adjoint between tensor and hom, it's pretty much the same thing. Okay, there is a very, very clear isomorphism between these two things. Okay? So we may identify this thing with this thing. And so you get a map from here to here, let's say. And what do you think this map is? I'm gonna let you verify the details. I wrote it down in the notes, by the way, but what you think this map is conceptually. This map here, look at it, is home or S applied to this thing. Apply that map. Let me just write down like this. Let's call this map, let's give this map a name because it's so important. Row. To row. Therefore, it is an isomorphism. And there you are. These two things are isomorphic. And therefore, if this is surjective, that is surjective. Okay? That's how you use matrix duality to transform an injectivity property into a surjectivity property. And voila. There you are. If your ring is complete, that's the key hypothesis here. That's the proof. And if you want to see the details of how this transforms, you can just look at it in the notes. But the reason should be there. Like everything here is just so canonical, so perfectly done that they have to agree with each other. It's always like that. There is no way how on earth can they agree, right? Like it would violate some very deep principle of the universe, right? So yeah, that's the proof. And so next time we're probably going to apply this to probabilities and see what type of notion we get. Okay, so thank you very much. No questions, I guess. Okay.